Good morning, friends. Today I'm going to talk about the traffic protection for the MPLS or ELDP or IP services. So before going into detail, let's understand how exactly this traffic protection came into the picture. Generally, we required it for the low latency services like VoIP, where we need the millisecond convergence time, because those are the delay sensitivity traffic. So if we go back to history, at that time we didn't have those requirement. So when everything was best effort delivery, and then recovery was completely depend on the routing protocols. Even at that time routing protocols were very slow, and end to end packet recovery was completely depend on TCP. But as time passes, we were looking for the faster convergence time. Then we tuned the IGP, where we were able to achieve within 1 second. But for the delay sensitive traffic, it was not sufficient. Then we pre-calculated the backup or repair path and push it to the fib level and diagnose the failure using protocol like BFD, and we try to achieve the convergence time within 50 milliseconds. So generally this 50 millisecond came from the SONET and SONET or ESDH protection, that was physical layer protection. This is how we evolved from the slow routing protocols towards the convergence time within 50 milliseconds. To achieve this fast reroute or the convergence time within 50 milliseconds, we need two things. First is the IGP, which is going to figure out the backup path and install it in the fib or safe level. And second one is to detect the failure as quickly as possible, which we can achieve using the BFD. So if we go back to point number 1, we have protocol like ISIS and OSPF. Which has the visibility of the whole network, or at least we can say within the domain, and based on that one they can figure out the best alternate next stop. Let's see how exactly they do. So if we see in this scenario, without protection it takes lot of time to update all those prefixes, and till that time customer will have impact. So if failure is occurred in his network, then it takes time to detect that failure. If router detects that failure, then it will propagate all that information into IGP, ISIS or OSPF. And then routers are going to run the SPF to calculate the next stops for that. So once router calculate the next hop, so it will try to push it to the SEP or fib level, and it will be per prefix basis. So it may take time if you have more number of prefix in the routing table. And once we push that information into the fib, then traffic will get restored. So you can see here in this figure, from T0 to T4, customer had impact. So until the primary next stops or the newly calculated next stops install into the fib level, customer will have impact for that one, and it can be from the milliseconds to seconds. And this was taking time again because of the flat fib structure. Let's see the scenario with protection. So we have enabled the protection in our network, and let's say that we detect the failure. So only we need to take time to detect that failure, and once we detect that failure, immediately traffic will move to over the backup path. So we can say that customer will have impact only from the T0 to T1, and in the back end all process will happen at the router level. That IGP will signal this event to all of its neighbor, then it will recompute the primary next hop, then it will update the fib table, and once it push that newly calculated path into the fib, then traffic will switch from the protected path to the newly calculated shortest path. To achieve the fast reroute, we have three options. One is for the RSVP FRR, RSVP fast reroute. Second one is the IP FRR that we called as a loop free alternate. And third one is the topological independent loop free alternative, that is the segment routing based. We will see it one by one how exactly it works and all the configuration as well. Let's see first how RSVP FRR protection works. So there are two flavors available for the RSVP FRR. First one is the link protection, that is we called it as NHOP protection, next hop protection, or the node protection, also we called is next to next hop protection. So this is the diagram which we are going to use for this lab. So we have the tunnel from P1 to P6, and this is the protected path, protected interface, and then backup path will be via this particular interface. So if we enable the link protection at the tunnel level, so he will send the RSVP path with the local protection required. So you can see this in the Wireshark snippet, where the P1 has set the local protection flag on, and based on that one, once P2 figure out that he has the alternate path available, he will send it RSVP path message towards P3, then P3 will send it to the P4 for the backup path, and for the main path from PE to path, RSVP path message will go from PE to P2 to P4, P4 to P5, and P5 to P6. So this portion is for the backup path, and this is the primary path. This is how it works for the RSVP path message. So once it reaches to the PE6, that is the tail end router, he will say that he is the last stop router, and based on the downstream on demand, he will assign the label and he will send it towards the P5. So he will set as an implicit null, he will forward it to P5. P5 will generate one label and he will send it to P4. P4 will generate one label and he will send it to P2. And same process is going to happen for the FRR path as well. And then P2 will send the label to PE1. This is for the RSVP reserve message. Then P2 will forward the label along with the note. He will say that local protection is available and he will send it to the PE1. So let's say PE1 is forwarding the normal traffic towards on the tunnel. So he will push the label which he has received from P2, and P2 will swap it with the label which he has received from P4. Same thing will go, and finally packet will reach to PE6. So we can see the trace route for this particular destination. Let's see how exactly it works in the case of link failure. So let's say that P1 is pushing packet with the 24001 label on top, and then the link between P2 and P4 goes down. So generally in the normal scenario, if any links goes down, that is without protection, if any link goes down, then the PLR router, which is P2 router, will send the path error message to our PE1, and then PE1 will bring down that tunnel. But in this scenario, we don't want to bring down that tunnel because we are rerouting that traffic via the FRR link protection tunnel. So in that case, some mechanisms should be there that P2 should inform not to bring down that tunnel. So P2 sends the path error where he will set the error code or error value as tunnel locally repaired. He is indicating to the PE1 that you should not bring down this tunnel because local tunnel repair is active. Based on that one, PE1 will not bring down that tunnel, but once he receives all those IGP update, he is going to calculate the new path for that tunnel. So once that interface goes down, two events happen. One is that path error goes to PE1, and second is that whatever packets are coming from the PE1, he is going to push it over the protected path. So whatever tunnel we have received from P4 on that interface, P2 is going to push that one in the bottom, and top label will be the FRR label. So P3 is going to forward it to P4 using the explicit null for this tunnel. So only we can see that 2400 routers labels which we were expected from on this interface. Same thing you are going to receive on the protected fast reroute tunnel, and it will swap with the label which he has received from P to P5, and he is going to forward, and P5 is going to use the penultimate hop popping, and he is going to send the packet to PE6. So you can see the trace route here, which is 24001. Then P2 has inserted two label. One is the normal label for that traffic engineer tunnel, and top label will be the fast reroute tunnel label. And then finally it will reach to P6, and once P1 gets the IGP update, he is going to calculate all those information. Based on that one, he is going to figure out the next best path for that tunnel, and once he figure out that next best path, he is going to push the traffic over that tunnel. Let us see how exactly it works. So if you see here, show run interface tunnel TE16. So this is the tunnel I have configured for it. So before that one, let's just check all this configuration or the show parameters. Before that, let's check some show outputs on the router level. Show ISIS agency. So I have agency up with the P2. Show MPLS interface, where it says that tunnel is yes and it's enabled. Show RSVP interface, it's enabled for the RSVP. Show RSVP neighbor, that is P2. Show RSVP session, two sessions, one is from P1 to P6 and then from P6 to P1. Show MPLS traffic engineering tunnels. We can see that this tunnel is up, and the second tunnel is from R6 to P6 to P1. Show RSVP interface, show MPLS interface. And if we trace route from here for the 6, we can see that here you can see the label difference, because just now I have bring it up the lab, so you can see the difference between the label here in the PPT and then actual label on the routers. So this is the label which we got from P2. This is the label which P2 got from P4, and this is the label which P4 got from P5. So on P2 we have configured the auto tunnel. So this is the interface which we are going to protect. This is interface gig 001. So auto tunnel backup and NHOP only, and this is the auto tunnel configuration we have configured here. So let's configure the fast reroute for this tunnel. Fast reroute, and then commit this. Once we commit this information, router is going to send the local protection required flag towards P2, and then P2 is going to calculate the backup path. If we see here, show MPLS traffic engineering. So let's verify the backup tunnel on the P2. Show MPLS traffic engineering tunnels, then auto tunnels. Let's check the tabular. So this tunnel T is 1002 is created automatically by P2 once he received the request from the PE1. So if you see the trace route from here, and if we check the tunnel configuration, so here we have enabled the fast reroute on head end, and on the PLR we have the auto tunnel configuration. Let's see what happens if we shut down this particular interface. This is the interface between P2 and P4 which we are protecting. So traffic should switch over to the backup tunnels. So you can see here R2 has inserted the fast reroute label, and then it has kept the same label which has received from P4. So this way link protection works. Now let's see how the node protection works. So this is the same diagram we are going to use. Only difference between link protection and node protection here is that node P1 is going to set the node protection flag on here, which will say that I need the node protection, which you can see here. It has said that okay, I need the local protection, but I need the node protection for that. And once P2 received that path message, he is going to figure out whether next to next hop or node protection is possible for him or not. If it is possible, then P2 is going to send this RSVP path message for the backup tunnel towards the P3 and P5. And for the primary path, P2 is going to forward that RSVP path message to P4. and this way both primary and backup tunnel will be up. So backup or FRR node protection tunnel start from the PLR, which we called as a point of local repair, till the merge point. So again, based on the downstream on demand, P6 will see that he is the end host and he is going to assign the implicit null label. P5 has assigned to 4000, P4 assigned again to 4000, and same process will happen over the backup tunnel as well. And then P2 will assign to 4001, but he will set that flag as he will set the information to P1 that yes, node protection is up. He will say that local protection is available and it is next to next hop, and he is going to send it to the P1. So the same way P1 is going to follow what we discussed in the case of link protection. So let's say P1 is pushing the packet towards the P2 and P2 has detected the failure. P2 is going to send the path errors towards P1 with the flag that local tunnel repair is active. Please don't bring down this particular tunnels, and calculate the next best path. And P2 is going to push to 4000 label, which P5 is expected from P4. Because P5 should understand this label, if we insert the label which we received from P4, P5 is not going to understand it. So we need to insert the label which we received from the P4 from the P5, that is 24000. So you will be amazed at how P2 knows that label. So while setting up the backup tunnel, P5 is going to send the label information on the reserve message in the record route option field. He will add that label information in the RRO and he is going to send it to P2. So P2 knows that in case of failure what exactly label I need to push. And then P2 is going to add the FRR label, which is 24003. P3 is going to remove that top label and he is going to send the 24000 label to P5, and P5 is going to do the implicit null and is going to forward it to the PE6. This way the node protection works. So if we see the trace route from the P1 at the time of failure, that you can see that you will observe the two label which P2 inserted. Bottom label is the label which P5 is expecting, and the top label is the FRR tunnel label. So let's see how exactly it works. Let me bring down this interface. If we see the MPLS traffic engineering, so we need to do one change here. Oops. MPLS traffic engineering, then interface gig 001 auto tunnel backup, and we need to remove this NHOP only so that it can calculate the next to next hop as well. Show run interface, trafficking tunnel 16, and we need to modify here fast reroute protection path protection node. Okay, so we are enabling the node protection here, and if we commit, then P1 is going to send the path message to our P2, which will say that I need the node protection, and P2 will act according to that. So before that, when if we check the trace route, okay, it's still going via 3. It needs to be re-optimized, so let's shut down the tunnel. Yeah, tunnel is up. So if we check the route entry for the RSVP-6, it will show that it's going via tunnel T16. So let's trace it and see if it is going via the P2 P4. Yes, it's going via the protected interface, that is via P2 to P4. So if you go through the configuration once again, we enable the node protection, and we remove that NHOP only from the auto tunnel backup so that he can calculate the next to next hop as well. So if we see here, show MPLS traffic engineering tunnels, auto tunnels, so if you see here, he has created 2 tunnels here. One is for the link protection, one is for the node protection. Here destination is R4, which is for the link protection, and then here destination is R5, which is for the node protection. But as we configured here node protection, it is going to use the node protection option here. So let's bring down the interface, protected interface, and let's say how exactly it works. If you see the trace route, so yes, P2 has inserted the extra label here, that is the traffic engineering tunnels, that is the fast reroute label, and then this label is the label which P5 is expecting, and once P1 gets all the IGP event updated, based on that one he is going to figure out the next base path, and he is going to move the traffic from the protected to the newly calculated path. Yes, we can see here the traffic has moved to the newly calculated path, that is why 2, 3, 4, 5, 6. This is how node protection works. And let's discuss the last option, that is end-to-end path protection. If you really need the protection, this is not the feasible option for you, because this is primary path and this is end-to-end protected path. So recovery will be completely depend on where exactly failure occurs and how soon P1 is going to detect it. If you have the failure far away from the P1, then definitely it's going to take time to detect it and then switch over the traffic to the protected path. But that's not the protection. So if we see here, if the link between P4 and P5 goes down, then P4 is going to send the message. Sorry for typo here, he is not going to send the local repair, but he is going to send the path error message. Let's say there is failure between P4 and P5. So P4 is going to send the path error message towards the P1. So it's completely depend on that path error message, how long it takes to reach to the P1. Based on that one, P1 is going to switch over it to over the protection path. Till that time, customer will have impact. So these are the three options. But challenge with RSVP is it's very chatty protocol. There is RSVP path message, there is RSVP reserve message, there are key for lives. This is okay for the small network, but if your network is growing big and big, so this RSVP is not scalable option. You need to set up the tunnel or session, and that tunnel or session information needs to be maintained on each and every node in the form of the soft states. So the routers will have the continuously keep alive message between those, and they need to maintain that or hold those states. So these are the major challenges with RSVP. Next we are going to see the IP FRR, that is loop free alternative option, in the next session.